Before I start this video, I want to preface, this video is not about the political history and nuances of real-life gerrymandering. Firstly, I don't have the background knowledge of that, and secondly, there are plenty of other videos out there that have already covered that topic. Link in the description to one that I personally found pretty helpful for that. This video is about a type of puzzle and some other mathematical constructs that I invented from the concept of gerrymandering. If you are interested in the puzzle side of this, go to these timestamps. If you are interested in the mathematical side of this puzzle, go to these timestamps. Without further ado, let's get into the video. Gerrymandering, defined by Wikipedia, is the political manipulation of electoral district boundaries to advantage a party, group, or socio-economic class within the constituency. In normal people terms, and in the context of this video, it's basically dividing up areas of land where people live in order to benefit a political party. The word gerrymandering itself comes from the year of 1812, when the governor of Massachusetts, Jerry Elbridge, signed a bill to create a new district, whose shape oddly resembled a salamander. Elbridge, Jerry, salamander. Together, they Steven Universe fused to become the word gerrymandering. I'm sure that many of you watching this video have seen this image floating around in the internet space somewhere. I know I've seen it a handful of times. It's a pretty simplified version of what gerrymandering actually is, but it gets the concept across pretty well. These individual cells are going to be called districts. I'm going to interchange between calling them cells and districts throughout this video, but just know that they are one and the same. These larger borders surrounding the groups of districts are called regions. When we look at the right side exclusively, you know what, let's just rotate this 90 degrees. Anyways, through this image, we can see pretty clearly that this simplified version of gerrymandering has two distinct ways it takes advantage of the division of votes. We have these two regions, which cram as many majority districts into a singular region as possible, which makes their respective power smaller. This concept is called packing, as it packs as many of the same voters into one district as possible. Then, we have these three regions, which have a fairly even split of majority and minority votes, where the minority votes barely win out in all three. This concept is called cracking, as it spreads out the majority voters into several districts so that they not only don't win, but just barely lose these regions. Combining these two strategies together, the minority voters are now in the majority in 3 out of 5 districts, which results in an unjust win. You can see fairly clearly how it's done here. Every majority district either overwhelmingly wins their region, to the point that they don't really win against anyone, or they just barely lose against the other side. In both cases, the majority voters' votes don't have much power, but the minority voters' votes do. Gerrymandering doesn't just go in one way to benefit the minority voters though. Looking back at the second chart in the original image, these regions have also been gerrymandered, as an even split would have 3 majority blue regions and 2 majority red regions. However, instead, all 5 of these regions have used cracking in order to make it seem like the blue districts have a unanimous win, when it's actually split 60-40. Now, looking at this grid and now understanding how gerrymandering works, doesn't this kind of look like a puzzle? At least, it does to me, where the goal of the puzzle is to gerrymander the districts into regions so that the minority wins. This specific configuration is pretty easy considering each type of district is all bunched up together. But let's try this configuration. Now things get quite a bit harder. Actually, you know what, let's change these colors first. The majority region will now be yellow, and the minority region will now be purple, just because I don't want this to be tied to actual political parties anymore. Before we get to trying to solve this board though, let's establish a couple of base rules. Rule 1. Regions must be comprised of districts that connect to each other horizontally and vertically. No diagonals are allowed. I add this rule because when it comes to gerrymandering real districts, they typically must be one single connected region, so no exclaves allowed. If we allowed diagonals, then we could get weird regions like this, where 2 regions cross over each other, and if these regions were actually drawn in real life, one would have to be disconnected, which again is not allowed. Rule 2. Each region must contain the same number of cells. In the previous example it was 10, however it can be any number of cells as long as every region is exactly the same. This also means that there cannot be any cells that are not part of a region. Rule 3. There may not be any ties, whether it's within the regions or overall. There must be one type of district that dominates all the others in a region, and there must be a number of regions that dominate the overall board. I've decided to add this as a rule because allowing ties severely overcomplicates things, so this just simplifies the puzzle a bit so that there's a more clear goal. That's really it for rules. Now we can solve the puzzle. Just to recap, the goal is to make it so that the purple districts win the overall election by dividing the districts into regions where there are more majority purple regions than majority yellow regions. pause here if you want to try solving it yourself, as I'm now going to go over how to get the solution. Alright, this probably seems like it'll be pretty easy, but when you actually begin trying to create the regions, it becomes quite a bit harder than you'd expect. Before aimlessly drawing regions and hoping it works out, you have to start with some math. The original red and blue example had 20 minority districts, but there are only 18 minority districts with 32 majority districts. First of all, the obvious thing to do to begin with is to start packing the majority districts. With only 5 regions to be created, we can pack 20 of the yellow districts into 2 regions that are entirely composed of yellow districts. Doing that, we have 12 remaining yellow districts and 18 remaining purple districts with 3 regions left. Again, since we're not allowed ties anywhere, these 3 remaining regions must all have purple win. Let's now figure out the math for these 3 remaining regions. We know that all 3 of these regions must contain a purple majority, and with 10 cells in each region, there must be a minimum of 6 purple cells in each region to secure a majority. 5 purple cells would result in a 5-5 tie with yellow, and 4 or less would mean yellow wins that region, which would then make 3 majority yellow regions, which is not allowed. Luckily, with 18 purple cells, they divide perfectly into 3 groups of 6, and the remaining 12 yellow cells divide into 3 groups of 4 perfectly, thus making a remaining 3 regions composed of 6 purple cells and 4 yellow cells. What this means is that there is no wiggle room in any of the regions. There must be 3 regions containing 6 purple districts and 4 yellow districts, and there must be 2 regions containing 10 yellow districts. Now we can get to solving the puzzle. One of the most vital pieces of logic that we can get from the math we did is that because every single purple district is in a region with 6 purples and 4 yellows, inversely it means that every single district containing a purple cell may not have more than 4 yellow cells. With that piece of logic is where we start, as these 3 purple districts on the left side of the board have quite a few yellow districts in between them and their other purple districts on the right side. In fact, look specifically at that bottom left purple district. Remember, this cell must be in a region with 6 purple districts and 4 yellow districts. If this purple cell connected with the top left purple cell, then that would make 3 yellow cells in that region already, and there's no way to connect to 4 other purple cells without going through at least 3 other yellow cells. Therefore, these 2 purple cells must be a part of different regions. Now again with this bottom left purple cell, if we assume it's not connected with the purple cell directly diagonal to it, then we can see that there's no way to connect it to 5 more purple cells without going through at least 5 other yellow cells, which again is not allowed. Therefore, these 2 purple cells must be a part of the same region. Now, in order to connect these 2 purple cells, the region has to go through one of these 2 yellow cells. We don't know which one yet, but right now that doesn't matter, as long as we know it's one of the 2. With that, we only have 3 yellow cells left allowed to be in this region, and we need to find a way to put 4 more purple cells in this region. Since we ruled out the top left purple cell earlier, there's now only 1 purple cell on the board left that these 2 can connect to without going through more than 3 yellow cells, which is this one. That means these 3 yellow cells have officially maxed out the number of yellow cells allowed in this region, and the remaining 3 cells must all be purple. As we can no longer add any yellow cells, it means these 3 purple cells must fill out the final cells in this region. While we still don't know which one of these 2 yellow cells is the 10th cell in this region, we do know that this yellow cell is part of an entirely separate region. Circling back to Rule 1, we know that every region must be composed of cells that are horizontally or vertically connected. There's only one way to connect the cell to any more cells, and it's through this pathway here, which is forced all the way until this cell. That now puts 6 yellow cells into this region, meaning this region must be one of the 2 regions composed of only yellow cells and no purple cells. That now means that these 4 cells must also be part of this region, since every other cell it can connect to is purple. That now clears up the ambiguity with the first region, forcing this top yellow cell to be the final cell in this region. With that, we have 1 of each type of region down, with 3 to go. Now, moving down to the bottom right, again with a connectivity rule, this cell has to be connected to these cells. This is where a bit of counting logic comes into play. Let's pretend that this group of 4 cells and this cell up here are part of the same region. When we do this, even without connecting them, we can see that this group of cells and this group of cells are now completely disconnected to each other. Since there's fewer than 10 cells in this group, we can't create another region here, which would mean that this group of cells must all be part of the region with these 5 other cells. This is not allowed, because if we combine these all into one region, this region now has 11 cells, which breaks Rule 2, since every region must have the same number of cells, which in this case is 10. But if we take any of these out, then they're now isolated and cannot be put into another region. That means that this cell definitively cannot be a part of this region, as no matter how you connect it, it will always leave at least one other cell isolated. With that cell a part of a 4th region, that now leaves 6 cells in this area, which means they all must be part of this region, and would you look at that, it gives us 6 purple and 4 yellows at the same region, meaning only one of each region type is left. Now, nearing the end, it gets pretty easy. This yellow cell has nowhere to go but out here, and all 6 of these purple cells must now connect to each other. That's pretty easy with these 5, but this purple cell all the way over here is still cut off. Since this region must also contain this yellow cell by connectivity rules, there can only be 3 more yellow cells in this region. And the only way to connect that final purple cell to this region is through these 3 yellow cells, finalizing our 4th region. That means that by default, these 10 yellow cells make up our 5th and final region, meaning we have officially successfully gerrymandered this board. Let's look at other board sizes now. Any square or rectangular board size can be gerrymandered with different sizes of regions and different numbers of regions. That's pretty obvious though, since it basically just ends up being multiplication. Like, the 5x10 we've been using can be divided up into 5 groups of 10 or 10 groups of 5. They both have the same minimum number of purple cells, as in both cases if you take any purple cell and replace it with a yellow cell, it no longer works. As already proven with the 5x10, the smallest number of minority cells there can be is 18 out of 50. But what about other size boards? Well, it's actually not that hard to find this out. Take any board size and color all the cells as the majority. For example, let's do 7x12. Split the grid into quarters by having the grid twice directly down the middle in both orientations. This top left corner will be our minority section, so change every cell part of it into a minority cell. But what about the ones on the edge? Well, if the line you drew is directly in the center of cells, round it up and make all of those minority cells as well. If the line drawn does split them evenly, you actually have to move it one to the right and make all of these minority cells as well. Doing this is so that the minority cells just barely win. Now you can see, whether you divide this grid into 7 groups of 12 or 12 groups of 7, the minority districts always win, just barely in every single case. I wanted to see what this would result in for many board sizes, so I made a chart for every size board from 2x2 all the way up until 14x14, and here it is. I thought that this would lead to something relatively interesting, and when I first created this chart, I sort of thought it did, as you can see there's these 2x2 chunks of numbers. Since each pair of rows and columns are exactly the same, I created this smaller version, and well, this is literally just a multiplication table, so that didn't end up really going anywhere. But then I realized, wait, this isn't correct. This chart assumes that the size of each region and the number of cells in each region must be equal to one of the side lengths, but in a lot of cases, these boards have more factors than that. For example, this 2x8 grid says that there need to be 10 purple cells in order for purple to definitively win. However, that is only if we divide the grid into 2 regions of 8 or 8 regions of 2. But if we divide the grid into 4 regions of 4, then we can actually get away with only using 9 cells. That makes this quite a bit more complicated to figure out, however, certainly a lot more interesting. With all of those cases in mind, here is the new board with board sizes that go up to 21x21. This is a lot of information to take in, so let me explain further how this is calculated. Let's take 10x16 for example. 10 times 16 is equal to 160. Find all of the ways that positive whole numbers can multiply to 160. For each pair of numbers, halve them. If the resulting number is a decimal, round it up. If the resulting number is a whole number, add 1 to it. This rounding and adding up is extremely important, as it means that the purple cells will always be slightly more than half of both numbers, i.e. the majority, which is exactly the same process we used in the grid division before. Then, find the product of these two new numbers for every single set. Once you've done that, select the smallest product, as that is the smallest number of minority cells needed, and that's pretty much it. As you can see, for the 10x16, doing 5 groups of 32, or 32 groups of 5 actually holds a solution that is better than doing 10 of 16 or 16 of 10, meaning the pair of factors that create the optimal solution for this board size is not the same as the dimensions of this board. This chart is a little bit daunting to look at, so let's highlight all the cells where the optimal solution is with a set of factors that are not identical to the board's dimensions. Boop! Now this is where things start to get pretty interesting. You can see several patterns emerge here, but there are a handful of anomalies across the board as well. Firstly, the most obvious one. In most cases, when the board size is the product of two even numbers, there is a better solution that exists. In every single case of this, one of the factors is an odd number. A lot of these patterns in the rows and columns just use the same odd number over and over again. For instance, the 18 column improvements all involve the number 9 as one of the factors, all the way up until 18x20. There are some places where even times even numbers do not result in a better solution though, and this is most notable when the board size is something times 16, but also 4x4, 8x8, and 4x8. This is also pretty easy to explain, as these are the powers of 2. All other even by even board sizes are getting better solutions because at least one of the numbers has odd factors that improve it, but powers of 2 don't have odd factors to pull from. So in a lot of cases, that means it cannot improve. Odd numbers are where it starts to get a bit more complicated. We can see pretty easily that prime numbers never have better solutions, apart from the earliest ones, 2, 3, and 5. 2 starts pretty instantly having better solutions for most of its boards, but 3 and 5 both are delayed, and I suspect that all prime numbers eventually have better solutions once you get to large enough board sizes. Odd composite numbers are where I'm really confused, because while they do have some sorts of patterns, there's not really any consistency to them. 9 only has better solutions with 2 and 4, and then with everything else it might as well be prime. 15 starts off like all the other even numbers, but eventually after 12 it just stops entirely. Then 21 is really bizarre to me, as it basically acts like the even numbers, except with even more optimal sizes with the lowest odd numbers and even less consistency than everything else. But let's look at this data in another way. Instead of just looking at which optimal solutions involve a pair of factors that are not equal to the dimensions of the board, let's look at how much better these optimal solutions are. Boop! Now, these odd composites are starting to have a much more distinguishable pattern, and one that is really strange to me. The amount the solution is getting better by is decreasing by 1 for each board size up when the other dimension is even. It's not just odd composites doing that though, look, 20 is also doing the same thing, with some inconsistency after a certain point though. Other even numbers such as 10, 14, and 18 are having some sort of consistency, but for some reason, 20 follows the pattern of odd composites. Okay, enough about this grid. This formula doesn't only have to be applied to square or rectangular grids, it can actually be applied to any number. Even prime numbers, although their optimal solution will always end up just being one group of whatever that number is, which means the optimal solution ends up being slightly above half of that number, but whatever. I generated what these numbers would be up to 500, and here is the result. As you can see, there's firstly this line of mostly prime numbers, which follows a line of pretty much x over 2, but again, slightly above that. There's also some composite numbers on this line, such as 178, because it doesn't have enough factors to make a better solution. We can also see another line in here that's directly in the middle of the lowest numbers, and the highest numbers, and all of these are numbers in which the best solution involves 4 as one of its factors. Then, on the very bottom, we have odd numbers whose best solution is the product of 2 other odd numbers. Instead of just looking at all of the outputs for this formula, let's also look at all of the actual distributions of the best solutions. In other words, which pair of factors results in the best solution for each number. Out of all the patterns I've found, this one is probably the most perplexing. Every fourth number, starting at 6, has exactly 2 solutions with extremely alarming consistency, as these are the only cases of numbers having 2 solutions. The only exceptions are 16, which should not be in this sequence but is because it has 2 solutions, which is just a weird edge case, and the numbers 18, 50, 98, 162, and 242, which all should be in this sequence but are not. I don't know why this is happening, but I do know how this is happening. Every single one of these cases with 2 solutions follows a pretty easy formula. Let's take 138 for example, which has 2 solutions of 3 times 46 and 6 times 23. If we label the first formula as x times y, then the other formula is always 2x times y over 2. This is the case for every single number in this sequence. However, when it comes to the numbers 18, 50, 98, 162, and 242, when you input them through this formula, they just result in the same thing but backwards. This is because y already equals 2x, so it can't be counted twice, meaning that this ends up being the only solution. Why doesn't this happen for other pairs of numbers though? For instance, 140 cells. 7 times 20 is the optimal solution with 44 cells, but putting it through this formula gives us 10 by 14, and that gives us 48 cells. Why is that? Well, there's one more thing that all these double solutions have in common, and it's that x and y over 2 are always both odd numbers. As we've seen before, odd numbers are always better for gerrymandering because the lowest majority of an odd number is always 1 more than the minority, whereas in even numbers it's always 2 more. There is one more exception to all of this though, excluding 16 as an edge case, and it's one thing that I truly cannot comprehend why it is doing what it is doing. The number 320. 320 is not in this every fourth number sequence. The numbers 318 and 322 are, and yet, for whatever reason, it is the singular number, excluding 16 as an edge case, not in that sequence that has 2 solutions. Even more bafflingly, its 2 solutions are 5 by 64 and 16 by 20, which is so close to being just like all the other ones, except instead of the 2 solutions being x times y equals 2x times y over 2, it's x times y equals 4x times y over 4. There's just so many things I don't understand here. Why is this the only pattern in which numbers have 2 solutions? Why are there never any instances of numbers having 3 or more solutions? Why is this pattern so insanely consistent beyond where x equals 2y? And why, out of that consistency, is there a single exception? What is it about the number 320 that makes it have two solutions? I actually asked some of my friends about this to see if they could find anything, and one of them found another instance like 320, being 5376, where the two solutions are 21 by 256 and 64 by 84. Also, it turns out 16 might not be an edge case after all, as it also follows this pattern of x times y equals 4x times y over 4, it's just that y also equals 4x. Looking at these solutions, every single pair of factors contains a power of 2, where that power of 2 is also a power of 2, so I'm guessing that that has something to do with it, but I'm not totally sure. Like, what do these other numbers have to do with anything? I checked every combination of 256 times something up to 64, and 21 was the only one that followed it. I still don't understand why any of this is happening, but at least we do have another case now. Anyways, that's enough data analysis for now. If anyone else notices anything or wants to continue extending what I've done, feel free to do so. I've only just begun to find these patterns, and as you've seen, there's still a lot I don't really understand, and a lot that can be extended, so if this interests you and you decide to look more into it, do let me know. Overall, I think this is a really neat concept that I don't think anyone has ever talked about before, and I would love to see people create their own gerrymandering puzzles, as I find it to be a really fun genre, both to create and solve puzzles for. Here are even more examples of gerrymandering puzzles that I made if you want to give them a shot. Remember, purple must win in all cases. That's all from me for now though. Well, actually, what if, instead of only 2 different color districts, there were 3?